All right, so today we're going to be finishing up chapter 23. We're going to finish up our discussion of electric potential. First, we're going to see our second Maxwell's equation. Then we're going to talk about how to calculate the electric potential of certain charge configurations. And then just a few odds and ends for potential. So let's first do a little bit of review. So yesterday, we saw that our potential of a point charge is given by this, 1 over 4 pi epsilon naught q over r. And then this looks a lot like the magnitude of the electric field for a point charge, because the electric field is just 1 over 4 pi epsilon naught q over r squared. So they look almost identical. And in fact, the electric field looks like the derivative of the potential. And that's because it is the derivative of the potential. So if I take the derivative of my potential, and remember the derivative, I'm in r here, my variable is r. So the derivative of 1 over r, remember, is negative 1 over r squared. So if I take the derivative of the potential of a point charge, I get negative times the electric field of that point charge. We can actually always write an electrostatic field, we can always write as the derivative of the potential, the negative derivative of the potential, because we have to put that negative sign in there. So this is very weird when you think about it, that an electric field, which is really a vector, right? It has 3 components. You can actually always write it as just the derivative of a scalar function. And now I'm being a little bit sloppy in what I'm saying, because it's not really just the derivative, it's actually the gradient. Now, if you haven't seen the gradient yet, that's fine. You can just think of it as a derivative, and this equation will do. If you have seen the gradient, we're going to talk about this more at the end. So if you have seen the gradient, you can write the electric field as the negative gradient of the potential. And that's because the components of the electric field are not all independent. So the components of an electric field have to obey certain constraints. For example, you'll never see an electric field that looks like this, because this field does not satisfy Maxwell's equations. So all of the components of an electric field, and later a magnetic field, are interrelated through the constraints on them imposed by Maxwell's equations. So we'll see that in some cases it's actually much easier to work with potential, because it's much easier in general to work with a scalar function than it is with a vector function where you have to worry about 3 different components. So that's why the potential is useful in electrostatics, because now we can just work with a potential, and then at the end of our problem, just take the derivative and get the electric field. So now we can get to Maxwell's second equation. So Maxwell's second equation is basically just what we did yesterday when we said that the electrostatic force is a conservative force. So this is Maxwell's second equation in integral form. So that just says the electric field over some closed loop will give you 0. The integral of the electric field over some closed loop will give you 0. And then in differential form, which is the more standard way when you see Maxwell's equations written, they're always written in differential form. It says that the curl of the electric field is equal to 0. Now the curl, I'm going to talk about in a second, but it kind of is just what it sounds like. It tells you how much does a vector field curl. So what this equation tells us, it tells us that an electrostatic field does not have any curl to it. It doesn't curl around anything, and we call that irrotational. It has no rotation in the field. So let's just get a little bit of a conceptual understanding of what curl is. So curl, let's say if I have a vector field that looks sort of like this, and we're going to see our magnetic field actually looks like this. So if I have a vector field that looks like this is clearly curling, right? There's some rotation here. This field has a curl, a non-zero curl. So the curl here is non-zero. Now an example of a field with no curl would be our electric field for a point charge, because this isn't curling around anything, right? There's no rotation here. So the curl here is 0. And similarly for our electric field of a infinite sheet that was just constant, like that, there's no rotation here, there's no curl, so the curl here is also 0. So that's all the curl is. You don't have to understand all of the vector calculus behind it. Just a simple conceptual picture will do. So first of all, what Maxwell's equation tells us here is that you will never see an electrostatic field that is curling like this. Now again, when we get into electrodynamics, it's a little bit different. When we have time dependence, we'll augment this a little bit. But for electrostatics, you will never see an electric field like this. The electric field is irrotational. It has no rotation to it. And actually, all conservative forces are irrotational. Gravity is also irrotational. And now why is this? It doesn't really seem obvious that if you have some kind of vector field that has no rotation to it, that it would necessarily be conservative. Or that if you have a field with a rotation to it, that it can't be conservative. So why is that? So let's think about a field with a rotation. So let's say we have some vector field that has a rotation. And just pretend it rotates like this, you know, all the way out to infinity. And I want to do a line integral around a closed loop. So I want to do that line integral. Let's just do let's just do some random field. So we'll just say some random vector field. We're doing a line integral around a closed loop. So when you do a line integral, you can think of it sort of as if there is a component of that vector field in the direction of your line integral. It will sort of pick up a non-zero contribution there. So if I were to integrate around this vector field from here around to here, my line integral is going in the same direction as my force, as my field. So this integral is going to be non-zero because, like, look at all this field that I'm integrating over, right? I'm integrating over all this field, so my line integral will be non-zero. So this line integral will be non-zero. And for the math majors in the class, I think there's like 2 math majors. I'm being a little bit sloppy with some of my nuances here, so just take this as a rough way to conceptualize this. So now let's take a field that has no curl. So we see that if you do a line integral around a field that has a curl, you have to get a non-zero answer. So right away we can see that this can't be conservative. Now let's see for the electric field something like this where I have no curl. Oops. So if I have no curl and I do a line integral around here, well, now you can see that at every single point where my line integral sort of crosses over one of my vectors from my vector field, they're perpendicular, right? And remember, the line integral, we have a dot product. So if at every single point where I'm integrating, my field and my line are perpendicular, that's just going to be 0, right? Everywhere, this dot product is 0. And now I chose 2 like very easy examples, but this is actually true for any field that has a curl or any field that does not have a curl. So that's why any field or any force that is conservative will be irrotational. It will not have any rotation like this because it necessitates that the line integral around a closed path in that field is going to be non-zero, and then it can't be conservative. So that's why the rotation of a field and Maxwell's second equation implies that the electric force is conservative. Okay, so now let's get back to potential. So we saw yesterday the potential of a point charge was just 1 over 4 pi epsilon naught Q over R. That's just a point charge. But what if we have a more complicated charge distribution? Well, there are 2 ways that we can figure out the potential for some arbitrary charge distribution. One way is by integrating over the charge, just like we did with the electric field where we integrated over dq. And then the other way to do it is by integrating the electric field. And we'll talk more about these 2. We'll do examples with both. So let's just look at the first way first. So yesterday, we said that the potential just adds, right? If we had the potential due to 2 different charges, we could just add the potential of each one together and get the total electric potential. So if we have just 3 charges here, we would just sum over each charge. But just like with the electric field, when we move to a continuous charge distribution, we have a lot, basically infinitely many little point charges, we're going to have to turn that sum into an integral. So now we're going to have to integrate over our charge distribution. And now one thing to be careful here is that yesterday I talked about a little bit about the reference point where we're setting the potential and the potential energy to be 0. So this formulation, when we integrate over our charge distribution here, we're implicitly assuming that our potential is 0 at infinity. So this, this formula here implies, this only works, so this implies that our potential is 0 at infinity. And we're going to see as we do later problems that when you have a finite charge distribution, this is the form that you're going to want to use to find the potential. And then when you have like an infinite charge distribution, like an infinite wire or an infinite sheet, you don't want to use this anymore. And we'll talk about why more later. So anyway, this formulation implies that your potential is 0 at infinity. So let's do an example with this. So it's going to be very similar to what we did for the electric field, except now it's easier because we don't have components to worry about. So we have a uniformly charged ring. It has a total charge of Q, radius A, and we want to find the potential at some point P, a distance x from the central axis of that ring. So this ring is just set with the x-axis going straight through it, and we want to find the potential at some point out here. So let's write down our equation that we're going to be using. So our potential is going to be 1 over 4 pi epsilon naught, and then we're going to be integrating dq over just r now. So let's actually not find dq yet, because we're going to see that this integral is actually pretty simple. So let's find r first. So let's plug in our r here. So r, it's already written for us, so we don't have too much to find. But so r is going to be just the distance from each point along our ring to that point that we're looking at on the x-axis. So at every point along our ring, since the radius isn't changing, the distance will just be x squared, whatever this distance is here, x squared plus a squared square root. So that will just be our r. So let's plug that in. Then we've got dq. Okay, and now we can cheat a little bit here because we can sort of see that our dq is not going to depend on a because a is fixed, so there's nothing to integrate there. And it's not going to depend on x either, since as we integrate around our ring, the x component of our ring doesn't change. It's just situated at x equals 0. So no matter what dq is, it's not going to depend on x squared plus a squared. So x squared plus a squared is going to be a constant. So we can just pull that right out of the integral. So let's just pull out x squared plus a squared. And then we're just left with dq. But we actually already know the integral of dq, right? Because we were told that the total charge of our ring was capital Q. So the integral of dq, we don't even really have to think about. It's just going to integrate out to total Q, right? So there's really nothing to integrate here. So this was a lot easier than our electric field where we had to worry about components and things canceling. We don't have to worry about that here. So our answer just ends up being 1 over 4 pi epsilon naught Q over x squared plus a squared. So you can see already how much the potential, doing things with the potential, simplifies them compared to the electric field. So if you said, what's the electric field of this charge distribution, the easiest way would be to just calculate the potential, since that took like 5 seconds, and then you would just take the derivative of this. So it's a lot simpler, and the components will just fall out of your gradient or your derivative. But we're not going to get too, like I said, we're not going to get too deeply into the gradient, since that's not really a prereq for the course. So anyway, you can see now how much simpler it is working with the potential just with this one simple example. So let's move on now to a line charge. So we have a similar problem where we have a charge Q spread uniformly along the y-axis from negative A to A. What is the potential at a point X on the x-axis? So let's write down our formula. And now here we do, we are going to have to do an actual integral. So let's do dq first. Let's figure out what dq is. So dq is going to be actually exactly the same as we did for our electric field when we did the electric field of this kind of charge distribution. You can see that our dq is situated along the y-axis, so it's going to be integrating with respect to y, dy. And then we have a line charge, so we'll just call that lambda. So our dq will just be lambda dy. And now let's figure out r. So again, r is kind of written for us here, so that's nice. So r will just be from each point, the distance is just the x component, or the x distance down here, plus whatever coordinate of y we're at. So we just have r is x squared plus y squared square root. All right, so now let's plug those things into our integral. So we have the potential is 4 pi epsilon naught. dq we said was lambda dy, and r we can plug in as x squared plus y squared square root. Okay, so now we can see that we do actually have to do an integral because we're integrating with respect to dy, and we obviously have a y in our integral. Now, the good thing is that we don't, again, actually have to do this integral because this integral is beyond the scope of what I would expect for you. So you can just look this integral up. If I asked this question on an exam, I would just give you like a table of integrals and you could just look up whatever integral you needed. So this integral you can just look up. And and I forgot to write my limits of integration will be from negative A to A since that's where the charge is located. So an integral like this, an integral of dy x squared plus y squared square root will come out to the natural log of x squared plus y squared square root plus y. So yeah, so just assume that this integral is, you can take it as a given. So now we have this. So let's just, well, I'll write that actually over here. Move that over here. Okay, so now we can sort of, let's see, let's evaluate, let's leave the constants out first and evaluate this. So I'm going to move my lambda out here so that I just have my integral to worry about. So this integral will just simplify to ln x squared plus y squared square root plus y, and then we're evaluating it from negative a to a. So that comes out to ln x squared plus a squared square root plus a minus ln x squared plus a squared square root minus a. And now we can rewrite, remember our logs, if you're subtracting two logs, you can write that as a division. So let's rewrite this as the natural log. Let me make this a little bit smaller. So let's rewrite this ugly thing as just one term so we don't have a bunch of subtraction things going on. So let's just write this as x squared plus a squared plus a over x squared plus a squared minus a. So that's what our integral will simplify out to. And now we can just, let's just rewrite everything. Let me add another page in here. So let's just rewrite everything so it's a little bit clearer. So we'll have 1 over 4 pi epsilon naught. We'll have lambda, and then we have the ln x squared plus a squared square root plus a x squared plus a squared square root minus a. And then let's replace lambda since lambda wasn't given in our original problem. Lambda will just be the total charge divided by the total length. Remember our line charge? So this we can just replace with the total charge divided by the total length, so that our answer is only in terms of variables that were originally given to us. So now we will have our potential is just equal to 1 over 4 pi epsilon naught q over 2a, and then ln x squared plus a squared square root plus a over x squared plus a squared minus a. All right, so besides the ugly integral, which, you would just look up anyway or plug into Mathematica, setting this up again was not that bad, especially compared to the electric field where we had to worry about components canceling, sines and cosines. The potential was pretty straightforward to solve in comparison. So let's now look at the second way to find the potential. Since the electric field, like we said, is the derivative of the potential, the negative derivative, if we're only in one variable of r, that means that we can integrate both sides, right? If I want to integrate both sides, that gets rid of my derivative from this side, and then I can just say, well, now my potential is the negative integral of my electric field. So that's exactly what we have here, and that's our second way of calculating the potential. So our potential between these 2 points, whoops, where did it go? So our potential between 2 points B and A is just given by the negative integral from A to B of the electric field. It's a line integral again. Now, one thing that's a little bit confusing in your book is this is what I would call the potential difference between 2 points, VB minus VA. And this is the way the integral would be set up. Your book flips it and does VA minus VB, and they call that the potential difference. Now, I can't really figure out what their rationale for doing it that way is. I'll obviously update you if I have like a revelation as to why they did it that way. Because this is the standard way. I checked my other intro physics books. They define it the same way as this. Any upper division electromagnetism book you look at is going to define it this way with VB minus VA. When you talk about a difference, you normally do final minus initial. So I'm not sure why they flipped it and called it VA minus VB. What I would recommend is if you're looking through your book and you're reading this chapter, do it this way, since this is the standard way. And I think just from my notes and discussion, we should be fine. You should be able to just skip this section in the book if you find it confusing the way they have it flipped a little bit. But they're the same. The physics is the same, I should mention. The book is not wrong. It just introduces extra negative signs, which is very confusing if you're a beginner. Okay, so that's my little warning with that. So let's talk a little bit more about this form. So remember, we are going to need a reference point. So typically, your VA is your reference point. So this is our reference point, and it will typically be infinity. Not always, but 99% of the time. And we will see a case today where it is not infinity. But 99% of the time, your reference point will be infinity, and that's where you're going to take your your potential to be 0. So normally, this is our reference point. So the potential at some location is just the negative integral from our reference point to the point where we're measuring the potential. All right, so let's do an example. So this is a very simple example. Let's say we just have a point charge, a positive point charge sitting at the origin, and we want to find the potential at some point r, some distance away from it. Now, we already know what the potential of this point charge is since I gave it to you in the last lecture, but let's just check that it's consistent with our integral form that we have. So let's say the potential at point VR. So let's say we want to do, so we have the negative integral of E dot dl, well, let's call it dr since we're just looking at one variable, dr. So my integral is going to go from infinity, my reference point. I start at my reference point, and then I integrate to that position r. So it will be VR minus v at infinity is equal to the negative of this integral of the electric field. Now, what's the electric field of a point charge? We know that. It's 1 over 4 pi epsilon naught q over r squared. So let's integrate this and just check that we get the same answer. So we've got negative 1 over 4 pi epsilon naught. Remember the integral, let's do the integral, we have q over r squared dr. The integral of 1 over r squared is negative 1 over r. So this becomes negative 1 over r. So I've got negative 4 pi epsilon naught, negative 1 over r, evaluated from infinity to r. So I can cancel out my negative signs, so we've got no more negative signs there. And now this expression here that we're evaluating, so this one we just have 1 over r minus 1 over infinity. 1 over infinity is just 0, so we're left with 1 over r. And we get the correct potential for a positive point charge. So, okay, this works out the way we expected it to. And like I said, our potential at infinity was 0. And I guess I should have technically done my little primes here to differentiate our variable of integration, but that's okay. All right, now let's do a slightly more illuminating example. So now let's consider a charged conducting sphere. So we've got our sphere. Okay, so we've got our charged conducting sphere. It has a total charge on it of positive q, and it has a radius of r. All right, so let's find the potential everywhere. So that means inside and outside the sphere. So let's start with outside, and we'll see why that's necessary in a second. So let's do outside, where r is greater than capital R. So let's write down our equation. We're going to want to do the, we want to do the negative integral of E dot dl. So what is E outside this conducting sphere? So this is, let me write it as E out because we want the electric field outside the sphere. So what is the electric field outside our conducting sphere? Well, we know it's just going to be the electric field of a point charge. So this will just be that of a point charge. So let's plug that in. We have negative, and I'll worry about my limits of integration in a second, 4 pi epsilon naught. We've got q over r squared, and we're integrating with respect to dr. So now, oh, this should be capital Q. So now what are my limits of integration? Well, I'm going to start at infinity, so I want to integrate from infinity, my reference point, all the way to whatever point out here I'm looking for the potential. So this is at some point r. So I'm integrating to r. Okay, so let's integrate this. So we're going to have the exact same thing happen as we had in the previous problem, where when we do this integral, we're going to end up with a positive 1 over 4 pi epsilon naught q over r. And so this is now our potential outside the sphere, so I'll call that V out. And now, what is my potential inside the sphere? Now you might think, well, my electric field is 0 inside a conducting sphere, so therefore my potential is going to be 0. But that's not actually correct. And we can see that this isn't correct because think about what I said, that the derivative of the potential is equal to the electric field. So I know that inside a conductor, the electric field is 0, right? But do I know that if I take the derivative of something and I get 0, do I know that that thing was 0? No, I don't. It was a constant, right? So that means that this is a constant. Now, that constant could be 0, but it could also be like 5 or 23.2. I don't know. The derivative of both of those will be 0. So that's why you can't just say, oh, my electric field is 0, therefore my potential is 0. Your potential will be a constant, and you have to figure out now what that constant is. So let's see how to figure out this constant. So what we can do, I'm going to bring my little sphere over here. So I've got my sphere here, and now I'm looking for a point in here. So this is my new location R. So we're going to do the potential is equal to E dot dl. And so now this is where you have to be very careful. If I were to integrate, I always integrate starting at my reference point. My reference point was infinity. Now I'm integrating to a place inside my sphere, R. But what electric field do I plug in here? Because out here, the electric field was the 1 over 4 pi q r squared. But then inside here, my electric field is 0. So which one do I integrate over? Well, I have to integrate over both because I'm starting from infinity and going all the way into this point R. So that's going to cover both electric fields. So what I have to do actually is my integral is really 2 integrals. So what I have to do is break it up like this. I integrate from infinity to the radius of the conducting shell, capital R, and that's my outer electric field, which we just did, where it's the electric field of a point charge. And then I have to integrate over my electric field that's inside the sphere from capital R to little r. And then I have my other electric field in here. So when you are integrating over a region where you have 2 different electric fields here, you have to make it into 2 different integrals, one over the outer electric field and then the other the inner electric field. And then that way you'll find what that V, what that constant is. So this integral, we already did the first one. We already did this one, and we know that it comes out to Q over R. But we're going to plug in capital R there since we're integrating to the radius capital R. So you can do that integral yourself if you want and convince yourself that you do get a capital R on the bottom there. But we'll skip that step for now. So this integral is going to come out to this. Now my second integral, I'm going to have minus, well, my electric field inside my conductor is 0. So I'm just integrating 0. So that is 0. So I'm going to put 0 here. So now I can see that my potential at this little point R inside the conductor is actually just a constant, right? Because everything here is a constant. It's just a constant, and it's the same as the potential on the surface of my conductor. And that's because, if you think about it, if the electric field is 0 inside a conductor, that means that the potential has to be a constant. So it's just going to be whatever value it was on the surface, it's just going to be that value all the way through. And this is why integrating from your reference point is so important. It's because if I didn't start integrating at infinity, I would have no way of knowing what the constant of my potential was in here. I just wouldn't have enough information to figure it out. So that's why you have to nail down your potential somewhere, nail it down at infinity, and you're saying this is where it's 0. So inside the conductor, the potential is 1 over 4 pi epsilon naught Q over R compared to infinity where it's 0. So let's just plot this out so we have a little bit better understanding. So I mentioned in a previous lecture that it's okay for the electric field to be discontinuous in certain circumstances. So if I was to plot the electric field for the case we just did, we know that the electric field is 0 inside the conductor, and then it jumps up at the surface of the conductor. It has a discontinuity, and the discontinuity is the sigma over epsilon naught, which is what we calculated a few days ago. So it has a discontinuity proportional to this, and then it looks like a point charge. So the electric field will always be discontinuous at the surface of a charged conductor. Now, if we graphed our potential the potential always has to be constant. So we'll never see a case in this class where the potential is not constant. So outside your sphere, your potential looks like that of a point charge. And then once it gets to the surface of the conductor, it's just constant inside. So your potential is just continuous everywhere. So I just want to emphasize again and really drive home the point that just because your electric field is zero, that does not imply that your potential is zero in that region. And again, that's because we said the electric field was the derivative of potential. So the derivative of any constant is going to be zero. So you can't say that if my electric field is zero, my potential is zero. All you know is that your potential was a constant. And this also means that since we know that the electric field is always zero inside a conductor, that means that the potential will always be a constant inside a conductor. Okay, and then let's talk about reference points a little bit more. So remember when dealing with gravitational potential energy, we could choose our reference point to be anywhere, right? If we were finding the gravitational potential energy of someone like throwing a ball off a building, you could choose your potential energy to be zero at the top of the building, or you could say, well, I'm choosing my gravitational potential energy to be zero on the ground. And both of those are perfectly legitimate. If you solve your problem using either way, you'll get the same final physical answer. And it's the same thing with potential, electric potential and electric potential energy. We can choose our zero to be anywhere. You want to choose it somewhere that makes sense, right? You want to choose it somewhere that makes your problem easier. And usually that easier choice is at infinity. So like I said, almost always we're going to be choosing our potential to be zero at infinity. And remember, this is because only differences in potential energy are measurable and meaningful physically. We never talk about the potential energy of just a single point. That doesn't have any meaning in physics. It's always the difference between 2 points that we want to talk about. And that's why we need a reference point, and we need an easy reference point. Oh, and just one more thing before we go on. I do want to just mention that, so typically you want to use this formulation when your electric field is either already known or really easy to find, like with Gauss's law. So if you have like some spheres or a cylinder, your best bet is going to be to use this scenario because the electric field is going to be really easy to calculate, and then you just have to take an integral. And we're also going to want to use this with our infinite scenarios where we have like an infinite line charge, and we'll see why right now. So let's see an example where choosing our reference point at infinity won't make any physical sense. So let's do an infinite line charge. So we have an infinite line charge somewhere of charge lambda. And we want to find the potential, a distance r, from this line charge. So like some distance r here. So this is our distance r, and what is the potential there? So we're going to want to use this formulation. And the reason for that is that right away, I know what the electric field of this is. So one thing I highly recommend is that you memorize the electric field of very usual charge distributions that we see a lot. And an infinite line is one that we're going to be using a lot, or an infinite cylinder. So definitely memorize the electric field for an infinite line. And also make sure that you know how to use Gauss's law to find it. So if you want to, so this would be a good time if you don't remember how to use Gauss's law to find the electric field of an infinite line or an infinite cylinder, just go back and review that because I'm just going to skip right to plugging in the electric field since A, you should memorize the electric field for an infinite line, and B, once you do enough problems, you'll just memorize it anyway. So this is going to be lambda over 2 pi epsilon r. So I can just plug that in right away. So let's plug in lambda 2 pi epsilon naught r, and then we're integrating with respect to dr. So what are my limits of integration here, and what am I going to choose as my reference point? Now, I'm just going to choose a random point as my reference point. Now, I know that that seems a little bit fishy, and maybe it is. So I'm just going to choose a random point at some distance r is equal to a, and say, all right, my potential is 0 there, and that's my reference point. And I can do that because I can choose my reference point to be 0 anywhere I want. So let's just choose it at some random point A. So let's integrate from our random reference point A to the point where we want to measure the potential. And let's bring out our constants. And we're going to see why we had to do this in a second. So now we're left with the integral of A to R, 1 over R dr. So what is the integral of 1 over R dr? Well, the integral of 1 over R is just ln R. So this integral becomes ln R evaluated from R to A is just ln R minus ln A, which again I can write as a division. So I can just write that as ln R divided by A. So now why did I do this? Well, what would have happened if I had chosen infinity as my reference point instead? So if I had chosen infinity as my reference point, then we would have had the integral. We would have had the integral from infinity to whatever point R, and this evaluates to ln R as we said. But what happens if we try to plug these numbers in? So I would have ln R, which is fine, but then I would have ln of infinity. And what's ln of infinity? Well, it's infinity. So that's not 0. And we definitely don't want infinity in our potential. So this would not be a good choice of a reference point because it gives us infinity. And the reason that this happened, the reason that we got this infinity here, is because really an infinite line charge is not a physical thing, right? In reality, we can have really long line charges that approximate infinite charges, but they're going to end somewhere. And you know, when we're doing these sort of theoretical problems, we can do things with our math that we can't really do in real life, and this is one of them. So it's because it's not really physical to have an infinite line charge. So that's why we got this sort of unphysical little problem here. So anyway, again, I know if this like confuses you, that's totally okay. I agree, it looks very suspicious. The first couple times I saw it too, I didn't really buy it, but think about it a little bit. Understand that it's because we're not really doing a perfectly physically realistic thing with an infinite line charge anyway. And in physics, infinities popping up are a big problem. So usually if you're doing a problem and an infinity pops up, it's because something went wrong. Okay, so now we have that all squared away. So let's just write down our final answer. So we have this negative lambda over 2 pi epsilon naught, and then we have ln R over A. Whoops, let me add another page here again. So we had for our potential, we had V was negative lambda over 2 pi epsilon naught. Now, it's better to just write this without any negative signs. So let's just distribute this lambda into this ln. That's equivalent to ln R over A to the negative 1, right? Remember our powers for logs. So R over A to the negative 1 is just A over R. So I can just rewrite this as ln A over R. And then I can just get rid of my negative sign that way. And I just have ln A over R. Okay, so that is our answer. And this way is also writing it as a positive is just a little bit better because we expect the potential when we're closer to a positive charge to be positive. So that's why I just moved that negative sign in there. All right, now let's figure out what is the potential difference between the plates of a parallel plate capacitor, each with surface charge sigma. So we sort of did a little bit with capacitors, or at least infinite plates. And just to remind you, a capacitor is just two equal and oppositely charged plates. One will have positive sigma, the other will have negative sigma. So let's say this is positive sigma, and this is negative sigma. And let's just say, we'll say that this is at y is equal to 0, and this is at y is equal to a. So we'll just set up a little coordinate system there. And that means our electric field will be going from the positive plate to the negative plate. So it'll be going like this. And let's figure out the potential between these two plates. So we're going to do E dot dl. Now you have a little bit of freedom here with like what plate you want to call zero potential. So I'm just going to call my negative plate my zero. So I'm just going to say that V is equal to 0 there because I can call it 0 anywhere. So now let's set up our integral. So I've got negative E dot dy, because now we're in the y direction here. So let me just draw, so this is y. So what's my electric field, first of all? Well, this is another electric field that you should memorize. The electric field inside a capacitor, inside two essentially infinite parallel plates with equal and opposite charge is something you should definitely memorize and know how to do with Gauss's law. So the electric field in between these two plates is sigma over epsilon naught. That's the electric field between two plates in a capacitor. In this case, the way I drew it, my electric field is pointing in the negative y direction. So I'm just going to put a negative y here. So, all right, let's plug these things in. So we have negative. My electric field is negative sigma epsilon dy. And I'm going to integrate from my reference point to my other plate. So I'm just going to integrate from my plate at 0 to my plate at y is equal to a. So I'm integrating from 0 to a. So I see that my two negative signs cancel out, so I'm left with sigma over epsilon. Those are constants. I have just 0 to a dy, and the integral of just dy from 0 to a is just y from 0 to a, which is just a. So my potential comes out to just sigma over epsilon times the separation between them. That's my potential. Another way, I could also just write this as the electric field between them times the separation between the plates. Either way is fine. And we're going to be using this a lot in chapter 24 when we do capacitors. All right, now let's talk about equipotentials. So an equipotential is a surface or a 3D surface, if we're in 3D space, or, since we can only draw 2D things, a line in 2D space, where the potential is constant. So if the potential is constant over some little path, remember the potential is the potential energy per unit charge. So that means that it would take no work to move a charge around an equipotential. So for the case of a positive point charge, the lines of equipotential are just concentric rings at each radius. So if you just move a positive charge, if we put a positive charge or even a negative charge, it would be the same. If you put a positive or a negative charge over here and just moved it around a circle of radius r centered around this positive charge, you would do no work, and the electric field would do no work because you're not changing the potential energy of the particle. You're not doing any work against the electric force. You can see the electric field lines are perpendicular everywhere to your little ring that you moved it around. So that means that everywhere the work done, F dot D, is 0 because it's perpendicular. So lines of equipotential, you don't have to do any work to move a particle along a line of equipotential. In the case of a dipole here, the lines are a little bit skewed when you're near the charges, and there's one equipotential line that just goes straight down the middle. So if you took another charge and just moved it straight down the middle here, you would have to do no work for that. And then in the case of 2 point charges, our lines of equipotential look a little bit funny. It kind of looks like ET actually. But I wouldn't ask you to draw the lines of equipotential for a charge distribution like this. Really, as long as you sort of can understand it in the point charge case, that's really the most important thing. And this means that all conductors are equipotentials, because remember, the electric field is always zero in a conductor, which means the potential is always constant, and by definition, if the potential is constant, that's an equipotential. So all conductors are equipotentials. So you do no work to move a charge around inside a conductor or on the surface. So now we have electron volt. So an electron volt is just basically a new unit of energy that you'll see pop up in some problems, and we'll use on and off throughout the rest of the class. So an electron volt is just the amount of work done on an electron to accelerate it through a potential difference of 1 volt. So like I said, we're not going to use electron volts too much in this class, but if you take higher level physics, they're used all the time. In particle physics, we actually give the mass of particles in terms of electron volts. You can convert this to like a mass unit, and you'll see a lot of times masses of subatomic particles are given in electron volts. So for example, you might see, if you're looking in some other books or in some other classes you take, you might see the mass of the electron written as 1/2 a mega electron volt. So we're not going to be doing masses in terms of electron volts, but it's important to remember for this class it's a unit of energy, and it's just equal to 1.62 times 10 to the negative 19 joules. All right, now let's do another example. All right, so for this example, we have a proton. It moves a distance of 0.5 meters in a straight line between points A and B in a linear accelerator. The electric field is uniform along this line. So we have an electric field that is uniform, and our proton moves from point A to point B, let's say over here. The electric field is uniform along this line with magnitude 1.5 times 10 to the 7 volts per meter, or let's write it in newtons per coulomb. And the electric field is also oriented from A to B. So determine the force on the proton. So that's easy, because all we have to do for part A, the force on a charged particle from an electric field is just Q times E. So we have the charge of a proton is just 1.6 times 10 to the negative 19. The electric field, we were told, was 1.5 times 10 to the 7. And just plug that into your calculator, and for that you get 2.4 times 10 to the 12. And this will be in newtons. And this force will be in the positive, let's say this is the x direction. It will be in the same direction as the electric field. Okay, and then for part B, what is the work done on the proton by this uniform electric force? So we don't have to integrate here, because it says that we have a uniform electric field, which means it's constant, so we can just do the dot product. So to find the work done by the electric force, we can just do the dot product here. So our force, we just found from part A, is 2.4 times 10 to the negative 12 newtons. We're dotting it along the same direction, right? The displacement is also in the positive x direction, the way we have it set up here. And it's a distance of 0.5 meters. So just multiply those two numbers together, and we get 1.2 times 10 to the negative 12. And this will be in joules. Now, if we wanted to convert this to electron volts, what we would do, so we have joules, we want to convert to electron volts, and there's 1 electron volt per 1.6 times 10 to the negative 19 joules. So our joules will cancel. We divide our answer we divide 1.2 times 10 to the negative 12 divided by 1.6 times 10 to the negative 19. And this will come out to 7.5 times 10 to the 6 electron volts. Now 10 to the 6 is a mega, so we can write this as 7.5 mega electron volts, which you'll see as MeV, capital M-E-V. Okay, so this is our work done by that electric field on our proton. Now let's find the potential difference between A and B. So let's write it this way. So we want to find VA, minus VB. So we can write this. Remember, our potential is the potential energy per unit charge, and here our unit charge, the Q we would divide, is the proton charge. So we can think of this as this difference here is the difference in potential energy between A and B divided by Q, and the difference in potential energy we can also think of as the work done between A and B divided by Q. So we have the work that was done, so we can just plug that in. So we have the work done was 1.2 times 10 to the negative 12 joules, and then we divide by 1.6 times 10 to the negative 19 coulombs. This number comes out to 7.5 times 10 to the 6 volts. So this is the potential difference if you do VA minus VB. So you can sort of think of this as the work per unit charge that the electric force does as it moves a charge from A to B, whereas the way that we think of it when we think of potential difference, we do VB minus VA. As I mentioned, your book does them kind of backwards. The difference really comes from whether you're thinking of an external force or the electric force. So writing it this way means that it's the work per unit charge done by the electric force. Writing it as VB minus VA will give you an additional negative sign, and the way you think of that is that it's the work done by an external force. Okay, so let's do one more example. So here we have a dust particle with mass 5 times 10 to the negative 9, which is 5 micrograms, and a charge of 2 nanocoulombs. So this little dust particle starts from rest and moves in a straight line from point A to point B. What is its speed at point B? So for this problem, you can tell since it has a speed in there that we're going to be doing conservation of energy and we're going to be looking at kinetic energy. So let's first write down our conservation of energy. So we've got kinetic initial plus U initial is equal to kinetic final plus U final. So it says that it starts from rest at point A. So right away we know that the kinetic energy initially is 0 because it started from rest. Then we want to find its velocity at point B. So we're going to be looking for, we're going to want to do 1/2 mv squared in here and find that v. Sort of just like we did in our last lecture. So now you might think that, okay, I see U there, so I'm going to want to use my formula for the potential energy of a system of 3 particles, but that's going to be a little bit cumbersome and not that easy, so let's do it a simpler way. Remember that the potential energy is given by Q times V. So in this case, Q, we're looking for the potential energy of our little dust charge, our little dust particle here. So our Q here would just be the charge of this little dust particle. And the potential that it's in is the potential due to this 3 nanocoulomb charge and this negative 3 nanocoulomb charge. So what we can do is write our initial potential energy as Q, the potential at A. And this is all equal to 1/2 mv squared plus Q times the potential at B. So I just used our other formula for potential energy since that's going to end up being easier. So let's first find our potential at point A due to these 2 charges here. So VA is just going to be the sum of the potential from each individual charge. So we've got 1/4 pi epsilon naught, we have 3 nanocoulombs, which is 10 to the negative 9. And just a little aside, definitely memorize all of your prefixes and suffixes. I don't provide that on the formula sheet. So like what a nanocoulomb is, I definitely expect you to know that that's 10 to the negative 9. Okay, so we've got 10 to the negative 9, and this point A is 1 centimeter from that positive charge. So we'll write 0.01. And then the potential at point A due to this charge here is negative, because we have negative 3 times 10 to the negative 9 coulombs. And then the distance, we have 1 centimeter and then another 1 centimeter to get to point A, so we're at 2 centimeters. And then just plug that into your calculator, and this number comes out to 1350, so 1,350 volts. So let's write that so that we don't forget over here. And now we're going to do the exact same thing for the potential at point B. So the potential at point B, we will do exactly the same. We've got from that positive charge, now the distance from the positive charge to point B is 2 centimeters. And then the negative charge is now 1 centimeter away from point B. And this number comes out to negative 1350. So the particle is moving from a place of potential with positive 1350 to negative 1350 volts. So now let's just add in another page here to do a little bit more algebra. So let me just rewrite our conservation of energy equation. We had Q of the dust particle, VA, is equal to 1/2 mv squared. This is our final velocity at point B, plus Q times the potential at point B. So let's solve for VF here, so we don't have too many numbers floating around. So we'll have QVA, we'll move QVB to the other side, minus QVB. That's equal to 1/2 mVF squared. I'll multiply both sides by 2, so I get 2 times Q. I can factor out my Q as well. 2Q times VA minus VB is equal to the mass times the velocity squared. I can divide both sides by my mass. And then I'm going to want to take the square root of both sides. So I'll take the square root of both sides. And so this is my final velocity. And just a general test taking tip, I'm sure you guys have heard before, it's always better to leave your variables like this and then plug your numbers in at the very end. That way, when we're grading it, we can very easily see where you make a mistake. If there's crazy numbers floating around, we can't find your mistake and we can't really give you extra partial credit points. So always try to keep your answer like this basically until the very end and then plug in your numbers. Okay, so now we can plug in our numbers. So we have 2 times the charge of the dust particle was 2 nanocoulombs, so 2 times 10 to the negative 9. Then our VA was 1350, right? Yeah, and then our VB was negative 1350, so minus negative 1350 is plus 1350, and then divided by the mass of our dust particle, which was 5 times 10 to the negative 9 kilograms. And then we take the square root of this whole thing, and the square root of this ends up coming out to 46 meters per second. Okay, so that's our final answer. So you can see that this little positive charge was accelerated from point A to point B because it started at velocity 0, and then at point B it was going 46 meters per second. And this makes conceptual sense. We always want to check to make sure that our answer makes physical sense, because when a positive charge is close to a positive charge, it does not want to be near that positive charge. When a positive charge is close to a negative charge, it wants to be near that negative charge. So it makes sense that our positive little dust particle was accelerated away from the positive charge and towards the negative charge. So this makes sense. So let's now just talk a little bit about some extra calculus. Now, I will not test you on this, so this is purely for fun. So I mentioned before the curl, and I should have little hats here. So we had our del operator. So I mentioned before our del operator, which is just a vector basically of partial derivatives. And so it's given by this, which I introduced a couple of lectures ago. So the electric field, or any conservative force, this is true for any conservative force that includes gravity, can be written as the negative gradient of a scalar potential. And a scalar potential just means a scalar function, and we just call them potentials. So a scalar potential. And this should also have hat. These should be x hats. That should be x hat, y hat, z hat. So now this is pretty crazy when you think about it, that a scalar function can encode enough information to give us the three components of the electric field. And that really is sort of one of the beauties of mathematics and physics, and it's sort of unexpected when you think about it, that vector calculus, where when you're taking vector calculus might be like, who needs this? Well, actually the electric field is a perfect example. And it's sort of, I think it's unexpected that the electric field and magnetic field would behave so nicely to the point of even using Stokes' theorem is relevant. So, because I know when I was taking vector calculus and we were doing Stokes' theorem, I was like, who cares? Well, this is why we care. So let's just talk a little bit about the connection between the curl, this scalar potential, and things being conservative forces. So the fact that we can write the electric field as the negative gradient of a scalar potential is directly related to the fact that the electric field is irrotational and has no curl. So these two things imply each other, the electric field having zero curl and being able to be written as the negative gradient of a scalar function. And this is because the curl of a gradient is always zero. So any function whose curl is zero can be written this way, because the curl of any gradient will always give me zero. And the way that we actually translate between our two versions of Maxwell's equation, where we had the integral form here, right? We had E dot dl, and then we had the differential form. We can translate between those two by Stokes' theorem. So that's a real-world use of Stokes' theorem in case you're ever like, why do I need this? So there's a lot of interesting things with the electric and magnetic field like this, where they really behave quite nicely in a mathematical sense, that they really didn't have to behave this nicely. So that's just some food for thought. That's the end of today's lecture. We will start dielectrics, chapter 24. We're going to be doing dielectrics and capacitors in our next lecture, and I will see you guys then.